Hello class. There was one more topic on displacement that I wanted to cover. Obviously, we normally would have covered this back when we were discussing displacement, but just with the way the schedules worked out, I couldn't cover it back then. But it is an important topic and I wanted to squeeze it in now. That topic is interferometry. The book doesn't really cover this too much and it's interesting, so I want to make sure I squeeze it in. The premise of this is that we use the interference of monochromatic light to determine displacement. By monochromatic light, I mean freaking lasers. If you have no idea what I'm talking about, you should YouTube Austin Powers and freaking lasers. It's a pretty funny video clip. I'm probably dating myself, but who cares? Or maybe I'm just going crazy, stir crazy with all the COVID-19 lockdown. But let's move on. Here on this screen, we have three different colors of, so these colors are different laser lights, and we have the wavelengths of those lights. So the red is 625 nanometer wavelength. Green is 532 nanometer wavelength, and blue is 450 nanometers wavelength. There might be a homework problem or test problem where you're going to need to use those, so those would be good things to include into your notes to remember. So here we have an interferometer. I'll kind of read through this text and walk you through what's happening. So a laser beam is split into two beams by a beam splitter. So the laser shoots out, it's of a certain wavelength, like on that previous slide. And then we have this beam splitter here, which could be a half silver mirror. So it allows part of the light to go through, part of it to go in the direction, part of it up this direction. Then number two, a fixed reflector provides a reference distance. That's this path. We'll pause at this point here, and we'll cover the second part of point two. So another reflector is affixed to a movable object. So we send the other half of that beam out here, and it reflects back, and it joins at this point. So this half silvered mirror has some of that pass through, and some of this path it deflects in that direction, but they do combine and come down here to this photodetector. So that's three. The light beams from fixed and movable reflectors recombine and interfere. That interference is dependent on the phase of light. I have a slide that's going to show this here in a minute. The displacement is determined from alternating constructive and destructive interference. Now let's look at that slide that shows the constructive and destructive interference. Probably familiar with this, but you have two signals that are in phase, they combine. That's constructive interference. If they're out of phase, they cancel each other. There's no signal when they're combined. So it's like it says here, the interference is dependent on the phase of light. If that movable reflector or the movable object is reflecting light back, if that moves, it's going to pass, every time it travels the wavelength of whatever light you're using, it's going to transition from constructive to destructive interference. There's actually a factor of 2 in there. We're going to describe that or explain that to you in a minute. But just get that concept that as one object is moving, the two are changing in phase relative to each other. So it's going to transition back and forth between constructive interference and destructive interference. So if we count those pulses, we can get the displacement based on the number of pulses. So we're going to get to that in a second here. Displacement systems use a photodetector coupled with an oscilloscope to measure light intensity. If the movable object translates a distance delta, and the path of the light beam increases by 2 delta, right? So this goes delta, but the light beam has to go delta and then delta back. So that's where that factor of 2 comes into it. This light intensity is important too, because we're not just counting the pulses, but we want to resolve down to get better resolution. We want to resolve down to 90 degrees, or some fraction of the 360. We don't just want to count the pulses. We want to resolve to values in between those. And measuring the intensity allows you to do that. So the number of successive occurrences of destructive interference detected by the photosensor is equal to the number of the wavelengths n. And if that is, well, I mean, that is the case. So based on that knowledge, we come to this equation. So it might be easier for you to comprehend this if you have the delta is equal to the number of those pulses times the wavelength divided by 2, right? Because the light is covering that distance twice. So counting n allows the delta to be calculated. And by resolving between just whole pulses, we might get an n that's n.5 if it was 180 degrees. Some number of pulses plus 180 degrees, plus another half of a wavelength change. Or phase shift, let's say that. So I'm not exactly sure why we have this slide again here. That main point, it was on the previous slide. I guess here we have it in a red box. That's the key to a lot of this. We're going to learn about some, this is the basis of this. We'll learn about some more modern ones, and it might not just be a 2 here, it might be another number, but we'll talk about that when we get to it. Just be aware of that. So here's a little bit of a note about that phase difference. So the phase difference can be correlated such that 1/100th of a wavelength can be resolved. So 3.6 degrees, right? 360 would be one period, so 1/100th of that. That means high resolution. If we're resolving down to 1/100th of a wavelength that's in the nanometers, and also there's that factor of 2 or more with some of the modern devices, that means really high resolution. So as an example of that, NASA's JPL developed a system with 20 picometer resolution. We're going to talk about something soon that's even better resolution than that. So other instruments, these so up to 0.15 nanometers over a 3-meter range. That's a more common instrument, not the top end stuff like NASA's. Okay, so we have one other thing here. Another advantage of it is it's a non-contact system. It's just light. You're not adding any loading error to it. Now I want to go, so we'll tell a little bit of a story here, go back to where this was first developed. Then we're going to jump up to the modern day with the same stuff. So we have this Michelson interferometer. This is basically the same as that schematic we were looking at. So this was named after a guy named Mickelson, and it's a little bit different orientation, but same concept as everything we described. So this Michelson guy and another guy named Morley, they conducted this experiment back at the end of the 19th century, like it's 1880s, 1890, somewhere around there. And that configuration was used to detect. So let me say this first. At the time, scientists, physicists all thought that everything that we were in this luminous, I never remember how they pronounce it. It's like luminiferous ether, something like that. So there was this medium that is what light waves propagated through. And we know now that that doesn't exist, but at the time they didn't know that. And they conducted an experiment. They wanted to, I'm not even sure exactly what they're trying to do anymore. They were trying to prove something along those lines, like maybe prove that ether was there or measure the fluctuations of it or something like that. But they ended up getting a result back that proved that that ether just wasn't there. And that led to a revolution in physics. And eventually it led to the theory of general relativity. So Einstein's special theory of relativity. Now I want to jump forward to LIGO, or the Laser Interferometer Gravitational Wave Observatory. So we have some pretty recent news from this. Somebody at MSU was really involved in this. I think he was involved in the analysis of the data collected. I should find out more about that. Maybe I could get him to come and talk to us one day when we're actually, it won't be you guys, maybe a future semester. But anyways, what they did, so they detected gravitational waves from merging black holes. Actually, funny, my son he's still in elementary school, but he's doing this science project and he was the thing, he's been really interested in black holes, and he picked black holes. We've been looking into this, and obviously most people think black holes are the explanations for what's being observed, right? They see these gravitational waves, but we found out they're, not all physicists believe that what we're observing is actually black holes. There's some very respected scientists, and what came up is dark energy stars, and actually just some interesting, like obviously I don't know if they're really black holes, if they're really dark energy stars, but some pretty cool stuff. They're observing the what's happening around whatever it is, and I think there's some promise that we're going to get some good images and resolve what's really happening there sometime in the near future. Anyways, it's interesting stuff. But what the LIGO thing did, it did detect gravitational waves, and they proposed that that's from merging black holes. And what this did was it confirmed an important prediction of general relativity, which is that there's space-time distortion in the context of large-scale cosmic events, which would make Einstein happy. I just thought that it was interesting that this interferometer was used 130 years ago to discover some evidence that led to the special theory of relativity. And then just recently, in the last few years, there's been evidence that confirms predictions of that theory. Part of why I wanted to cover this topic. I did some work at Princeton. It was quite a few years ago now, but when I was there, the guys I was working with gave me a tour of this room. This was Einstein's classroom, and they've basically left it as a museum. They haven't touched anything. You see, all this was per what Einstein wanted, and they still use it as a classroom. It's just because of the historical importance of it, they haven't modified the architecture or any of the built-in equipment in it. I did stand there and give a short lecture, and people just laughing at me. I just want to say that I had given a lecture in the same spot as Einstein. Obviously, I don't compare, but it was, if you have the opportunity, got to do it, right? Now, on to that Michelson Morley versus the old one versus the LIGO one. The Michelson Morley one had arms that were 11 meters long, or roughly 33 feet. And the LIGO one, the arms of that are 4 kilometers long. And so it's the largest ever built. Part of it, the laser just travels further, which makes it more sensitive, right? If it has to travel further than those distances, we end up getting a better resolution. But it goes much further than just the longer distances. It also, so there's a couple characteristics that we're going to learn about. The first one is the Fabry-Pro cavity. So this adds mirrors here, and not only does it go those 4 kilometers, but it also gets reflected back and forth. And in the LIGO one, it reflects it back roughly 280 times. So 280 times 4 kilometers before they merge together again. And so this is an important thing to point out. So the 2 in our equation in that case then would be replaced with, it'd actually be, you have to be careful with the wording, but if it reflects it back 280 times, so we normally it would go once, but then if it's 280 times, we want to make that, so once would be 2 in our equation, right? But if it goes 280 times, then we want to make it 280, or it might be 281 if it didn't include that first one. Just be careful to the wording in that if you solve a problem. And I'll give you an example of that coming up soon here. But the Fabry-Pro cavity was one thing. So that makes 280 times 4 kilometers before merging together. That's 1,120 kilometers, or 144,000 times the original. And then another thing, it also needs a power boost. So if I don't know how far I have to go back. Actually, I think I can probably go forward. Yeah, here we go. So in this old one that we're looking at, you saw that, so the reflected path comes here, part of it gets through to recombine, but part of it gets deflected this way and is essentially lost. And then here, same thing. Part of it's deflected down here to get recombined, to be sensed, but part of it is let through and just lost. So the thing that they did is they put this power recycling mirror in here. And this essentially just feeds that energy that would have been lost back into the system. So that helps give them that power boost that they need. Maybe I just only put this in here to cover just to show you the energy being lost. So let's move on to the next slide. This is the example. So you're using an interferometer with a blue laser to measure displacement. Like the LIGO interferometer below, your interferometer has Fabry-Pro cavities. Your cavities reflect the light back to the displaced object 24 times. Your photosensor reports 38 pulses and an additional 90-degree of phase difference. What was the displacement? So I'll probably go back and forth here a little bit. Maybe I transferred all of it over here into my chicken scratch. But we have the laser, and here I'm just kind of showing conceptually these reflections. So normally the laser would go through and it would come back. That would be just our normal path through a basic interferometer where 2 times delta equals the number of pulses times the wavelength. But the wording here is the photosensor, no, not that. Your cavities reflect the light back to the displaced object 24 times. So we have our normal one that goes through, and then this reflects it back 24 times. So we're actually going to have 24 plus 1, right? Because we had the normal one plus 24 reflections back. So our n is going to be 24 plus 1. And so normally we would have 1 times 2, but here we have 1 plus 24 times 2, so we'd actually have 50. That's what we want. Our 2 would have to become a 50. So So 2 delta equals n wavelength is the basic interferometer, covers delta times 2. This interferometer covers the normal one plus 24 reflections back. So 25 times the 2, which is 50. So 50 instead of 2. And then also we're told that it's 38 pulses, and then it also senses an additional, 90-degree of phase difference. So 90 divided by 360, that would make our n equal to 38.25. So we rearrange for the delta. We have 38.25 times the wavelength of the blue laser, which we were given right at the very beginning of this lecture, divided by the 50 equals 344.25 nanometers. That's how much that object moved. I want to show some other modern applications of this. So this would be 3D scanning vibrometry. Let's follow this link.
Developing safe, reliable and appealing products is an enormous challenge. Structural testing, FE correlation, experimental modal analysis, operating deflection shape analysis and NVH optimization are critical processes for product design, development and manufacture. In a fiercely competitive world, vibration measurement can be a powerful and sophisticated tool to create a winning product. Discover the advantages of 3D scanning laser vibrometry and learn how vibration measurement is done quickly and effectively with superior technology from Polytech. Laser vibrometry uses the Doppler effect for non-contact optical vibration measurement. The effect describes how the frequency of light is changed slightly when the light is scattered from a moving object. Within a Polytech vibrometer, a high-precision interferometer detects the minute frequency shifts of the backscattered laser light. To achieve this, the interferometer splits the light into 2 parts. The so-called reference beam propagates directly to the photodetector, while the measurement beam is incident on the test object, where the light is scattered by the moving surface. Depending on the velocity and displacement, the backscattered light is changed in frequency and phase. The characteristics of the motion are completely contained in the backscattered light. The superposition of this light with the reference beam creates a modulated detector output signal, revealing the Doppler shift in frequency. Signal processing and analysis provides the vibrational velocity and displacement of the test object. Vibratory motion is properly characterized as a true 3D phenomena. A complete measurement using Polytech's 3D scanning vibrometer includes the spatial nature of the motion. Vibration measurements help unravel the critical system dynamics of a test object. The 3D scanning laser vibrometer uses light as the sensor, eliminating the influence of a traditional contact transducer on the test object motion. By using scanning mirrors, the light is sequentially placed on a grid of points, measuring the motion of a complete surface. 3 measurement heads sample each grid point in 3 separate directions, uniquely determining the vector motion at that point. Vibrometers deliver meaningful results. Real-time data help to visualize the temporal signature, and frequency spectra display the characteristic resonances. For full field measurements, spatial deflection shapes are visualized as an animated pseudo-color representation, or as a dynamic 3D graphic for a better understanding of the overall system response.
So we have one of these within the department. Professor Jenkins was using it to study guitars. So this is some of the measurements he made. He was trying to basically determine what makes an acoustical guitar sound good and what makes an acoustical guitar sound bad. And then there's that field is maybe a little bit more art. There's definitely some science in it, but more trying to make it a quantifiable engineer's view of it all. And anyways, this is some of the data he collected. He just was looking at resonances of acoustic guitars, and you'd look at how they're built and try to correlate the construction techniques with the resonances. This is a pretty basic resonance. So if we go between these two, you see, so the red is that it's pumping out towards us, and the blue is that it's going in away from us. So, whoops, it's just going back and forth between those two modes. If you went up in a higher frequency, these would get much more complicated. Last I heard, I think Professor Jankowski has that now. I'm not exactly sure what he's doing with it, but we have it within the department. You might want to talk to some of those guys if you're interested in that type of a thing. So this is how they used to find resonances in guitars. Chladni plate. This makes a pretty interesting demo. So this is an old one where they excite it with a violin bow. I use one of these in my acoustics class, but I don't excite it with a violin bow. Instead of this stand here, I've replaced this with a speaker, so I can it's just a speaker driver, so I can send whatever frequency signal I want to it. I can change the amplitude, I can change the frequency, and I can excite it at different frequencies. And the idea is that the parts of it that are vibrating at a mode, these sand particles will move away from those, and they'll rest at the nodes where it's not moving. Anyways, that's that. So this lecture's done. We'll see you later.